We have a sample problem here. A single paned glass window in a building has dimensions of 2 meters by 1.5 meters by 3.2 millimeters. The temperature inside the building is 18 degrees Celsius and outside the building is 14 degrees Celsius. Calculate the rate of heat flow through the window. So this is an example of conduction. Our equation for conduction, thermal conductivity, cross-sectional area over length, and then this difference in temperature. All right, so a glass window, I need to come back to the test notes. Glass, it might be really hard to see. Feel free to grab your test notes. Glass has a thermal conductivity value of 0.8. 0.8 watts per meter times Kelvin. So we have this value for glass. The window is, I don't know which dimensions are 2 by 1.5, but those would represent the outside, the rectangular dimensions. The 3.2 millimeters would be the thickness. So that would be our L. That L in the equation is essentially the length, the distance the energy is going to travel to get from inside to outside, because the energy is going to flow naturally from the hotter temperature to the cooler temperature. So the area would be the area of this rectangle, so the 2 by 1.5. Delta T is the temperature difference between inside and outside. We typically take the hotter temperature minus the cooler temperature just so that we get a positive value. So if we plug these numbers in, so 0.8 watts per meters Kelvin, area 2 meters by 1.5 meters. L, we will want this to be in meters. And then delta T, the difference in temperature is going to be 18 minus 14. Because remember, any change in temperature, we get the same answer if both temperatures are in Celsius or if both are in Kelvin. So this I can label as Kelvin, which in turn is going to cancel with the kelvins in the thermal conductivity. I have 2 meters in the denominator, which are going to cancel with the meters in the numerator. And that's going to leave me with just watts. The watts is a joule per second. We can leave it as watts in our answer. Or if we prefer joules per second, we can write it that way as well. So 3,000 joules per second would be the rate of heat flow through this window. Now, if you know anything about windows, I'm not an expert in any way, but in homes now, we don't use just single paned windows. We may have double paned or even triple paned. It depends upon the builder and all that. So a double paned window means I have a piece of glass and then a thin layer of air, which it doesn't look very thin in my picture, but then another piece of glass. So when we talk about inside versus outside, the energy has to flow through the glass, then through the air, then through the other piece of glass. Well, going back to the test notes here, air, now this does assume 20 degrees Celsius and 1 atm. But in general, this K value is smaller by quite a bit, 0.023 versus 0.8. That means as the energy moves through the air portion, that air portion slows down the heat transfer. It doesn't allow the energy to transfer as quickly. So by having double paned windows or triple paned windows, we are making the home more insulated. We're slowing down the rate of heat transfer between inside and outside, which makes things more efficient. So the energy we're using to either heat or cool our homes is staying in our homes better than it would with just a single paned window.